I don't know, maybe you will or won't think. But like I said, now we're going to focus on our solar system. But before we focus on our solar system, we're going to kind of take a look at the contents of our solar system again. Each one of these slides is going to kind of talk you through the sun and the planets and that sort of thing. And these slides I'm going to show you oftentimes has key information that we're either going to hit again when we talk about that planet or it could be on your test, that sort of thing. But, okay, at a glance, not drawn to scale, and we'll be talking more about it, but if I draw a break right there, why would I draw a break between Mars and Jupiter?
Isn't that where an asteroid belt is?
There's an asteroid belt there, exactly. And what else? Are these guys any different than those guys?
They're bigger.
They are bigger, exactly. I like that. These are giants. And I like the other thing. My break could be the asteroid belt. That kind of does it. Belt. Oops. Let's see. I'll give you another thing to think about. Have you ever heard they're giants and they're gas giants? Dude. Okay. And these are kind of what we call rocky. Yeah. Not like Rocky and Bullwinkle, but rocky. And, oh my gosh, when you get out here, the spacing is crazy in that it's just wide space when we hit Jupiter between planets. Just crazy. One semester, I had me and a group of students, actually, we walked out, relatively speaking, how close the planets are. And so we started at, what's this little school up here, kind of?
Hawthorne?
Thank you. Started like near Hawthorne. And we put a volleyball, kind of the size of the sun. And then to scale, we kind of ended with our rocky planets about to this driveway. Okay, and then we started marching off the gaseous planets. Okay, and we ended up, we would have had gone past, is this like Messenger Road up here? No, this is Messenger. What's that? Plank. Yeah, we would have to go clear up to Plank. So, anyway.
Something like that in the museum, whatever it is, in Washington, D.C.
They had to kind of give scale to it.
Yeah, like it started way down here, and we went there over the summer for a school thing.
That's cool.
And they made us walk from here all the way over, way over here.
And was that supposed to represent like the edge of our solar system, or the?
It was from the sun all the way out to that smaller planet past Pluto.
It's a hike. Yeah, Eris maybe.
Yeah.
Yeah.
It wasn't fun.
But it made an impression.
Yeah.
So actually, we'll dive into this. We won't dive into the sun, but we'll talk more about the sun in, I think it's the Unit 3 in here. But one of the things we already talked about the sun is that it is using Einstein's relationship, that converting M as matter into a bunch of energy. Okay, kind of described. Yeah. So. Most of, and we'll be talking more in this unit of material when we talk about the formation of our solar system. It's got a bunch of hydrogen and helium. All right, so a slide for each planet-ish, kind of. So Mercury, do you see where, and that is the true color of Mercury, okay? Look kind of like the moon, kind of gray, kind of desolate. Yeah, kind of pocked like the moon. And we're going to kind of talk about these cliffs on Mercury. Probably came about when it was cooling. I guess the other thing that's striking is, you know how the Earth spins, okay? And you guys would say that the side of the Earth facing the sun is daytime and nighttime, right? Okay, daytime and nighttime. If the sun's over there, this is the Earth. Well, the thing about Mercury is it has a daytime side and a nighttime side. But Mercury spins so slow. It's kind of like you have a chicken on a rotisserie, but the rotisserie is just not very fast. So the daytime side of Mercury is just very hot, okay, the daytime side. And the nighttime side is so very cold. Just strange, okay, very strange. Then we have Venus, okay. Okay. The thing about Venus is it's got a bunch of clouds. Okay. Very heavy with regard to clouds. In fact, we don't see the surface of Venus like we saw the surface of Mercury. But with that said, and it was the Soviet Union that actually chose to go to Venus, okay, years ago in the 70s. And they have a spacecraft that successfully fell through the clouds, landed on the surface of Venus, and sent back some pictures before it died. Or the aliens got to it, one or the other. Okay, so Venus is covered in clouds. The clouds actually then trap heat. The clouds trap heat, okay? And so it is very toasty. Notice that it's totally in contrast to Mercury with regard to kind of the day and the nighttime, the hot daytime, the cold nighttime temperatures. It's just hot everywhere. Okay, Venus is very hot. Sometimes we like to think of Mars as our sister planet, but actually Venus is more similar to Earth than Mars. Then we have Earth, okay? So the planets going out go Mercury, Venus, Earth, Mars, right? So Mercury and Venus have no moons. Mercury and Venus, no moons. Earth, beautiful moon. Uncharacteristically beautiful, okay? And we have liquid water. And so we have life. Then we get to Mars. Okay, so I was listening to somebody describe the situation at Mars right now, you know, with the two satellites recently getting there. And it's like Mars is like a traffic jam with regard to humans sending stuff there. Well, that was kind of an interesting way to think of it. So this is a rover. This might be one of 3 rovers. I'm kind of thinking it's the most recent one. Called, let's see, Spirit, Opportunity, and, dang it, it'll come to me. But anyway, it's a rover on Mars. Okay. Then we have the asteroid belt. But then after the asteroid belt, we have our first gaseous or Jovian planet. I mentioned Jovian. We call it a giant gas planets, or sometimes we call them Jovian. It's the same thing. And it's humongous. It's the biggest of the gas giants. Okay, so you need to put 300 Earths inside there with regard to the mass. Now, I missed Mars. Do you guys think Mars has any moons? Does Mars have any moons? How many people think it does have moons? It does. It does have moons. It has 2. Mars has 2 ugly-looking moons. Poor thing. Then Jupiter's got beautiful moons and probably some ugly-looking moons. But all the gaseous planets, all the giant gaseous planets have moons. And actually, this is looking from one of Jupiter's moons toward Jupiter. This is the moon Io. So the thing about Io that I think is so cool is that through his telescope, Galileo saw Io. Isn't that neat? No. And the only reason we see Jupiter or Saturn or Uranus, or the only reason we see Venus or Mercury is because sunlight is landing on them, and that sunlight is coming back at us. So it's the same way with the planets and the planets' moons. So when we talk about Jupiter in this unit, one of the things I'm going to emphasize is, can you tell me the 4 moons that Galileo saw? And listed in order of closeness to Jupiter: Io, Europa, Ganymede, and Callisto. Now, I've heard those pronounced different ways. That's how I pronounce them. And actually, we can land on these. We can land on these. And so, actually, this is where we might be more likely to find life. We can't land on Jupiter itself. We haven't yet. I'll show you the next slide coming up, or the next slide coming up to show you where we have landed. We have landed here. Boy, I'm trying to think of what what was the... I'm drawing a blank with my spacecraft. We have landed here. Spacecraft has landed here. This is a moon of Saturn, and it is called Titan. What was the name of that? It's all going to start to come back to me. Can you kind of see the fuzz around the moon of Saturn? So Titan is unusual in that it has an atmosphere. So there you go. And Saturn's beautiful. A cool feature about Saturn is, do you see the shadow over here? Okay. So basically what we do is, in this figure, we have the sun over here, and the orb of Saturn is casting a shadow on part of its rings. Isn't that beautiful? Oh my gosh. It's just wonderful. Okay, so Saturn's rings, this actually is an artist's rendition of what you would see if you were traveling through Saturn's rings. Okay, they're not like solid. They're like a bunch of little rocks. Not just plain rocks, but they're icy rocks. Okay. Okay, so we had Jupiter, Saturn, Uranus, and Neptune. So a lot of times you'll see Uranus looking like it's kind of lying on its side. Okay, and this actually is on purpose. It is spinning around an axis that basically lies in the plane of the ecliptic. It's kind of weird. So if we kind of look at the Earth's axis of rotation tilted 23.5 degrees. Okay. Uranus's axis of rotation tilted about, I think it's like 89 degrees. Okay, almost 90 degrees from being straight perpendicular. So that means that if we put the sun here, put my trash can here, Uranus's north pole might go like this, and then this is a quarter of its year, okay, and this is half of its year. So you talk about some strange seasons. Yeah, this is 3/4 of its year, and here it's back, and it's spinning like this. So strange. And then we have Neptune. So did you kind of catch the color of Uranus and Neptune is kind of blue? They're kind of sister planets, and that's from the same kind of gas that's in their atmosphere. And actually Jupiter and Saturn are kind of orangish, reddish, and that's because they have kind of a similar. So we kind of have them in pairs out there. So when we take a look at Neptune next week, or it might be next week or maybe a week from Monday, one of its moons is called Triton, which drives me nuts because do you remember I said just a minute ago Titan? That was the one that kind of had a fuzzy look around it. Titan is a moon around Saturn, and Triton is a moon around Neptune. You can have a nut card. So, can you see the little ring around Neptune? Actually, I think all of these figures I've shown you, beginning with the gas giants, have rings. They're not as cool as Saturn's rings, but all of the gas giants have rings. They all have moons. Okay. Then we get to Pluto. Pluto and Eros. Actually, just Pluto. Pluto's not a full-fledged planet anymore, but it's a dwarf planet. Embrace it. And I double-checked last night, but the New Horizons is going to be at Pluto in July 2015. And I hope you'll think of this class then. New Horizons. And I'd also double-checked because somebody was like, well, how long did it take to get there? And it was put up in space in 2006. So, yeah, it's going to take, then, 9 years. Not too bad. And then that same person said, well, if we were going to go to the moon, how long would it take our spacecraft to do the whole moon thing? 3 days. Of according to the site I looked at. So I thought that was interesting. Okay. So can you see the plane of the ecliptic there? Does that look like a... Good. So the Earth orbits and all of the other planets orbit in a nice kind of disk sort of thing. It looks like, see, people are going to start to forget what records really are. The vinyl records, although maybe they're coming back, but it's kind of like a record, and there's a different tracks on the So as we kind of talk about the formation of this, what we call our system of planets around our star, the sun, we need to take in consideration kind of some oddities, all of the features. It's just like the makes sense scientific method. You have your observations, and your observations need to be consistent with your explanation of how the solar system came to be, basically. So one of the things I've been talking about is counterclockwise, right? Okay. So what that is basically if you look down kind of at our frisbee, we call the solar system, the sun and the planets, we got a bunch of counterclockwise going on. The sun is actually spinning on its axis of rotation. Okay, there's a dot there, the sun's spinning. The planets are spinning on their axis of rotation. This could be Mercury, or this could be Jupiter. This could be Mars. Okay, so we got the kind of counterclockwise thing. So we need to kind of explain that, and that's not too bad to explain. Another thing, ultimately, and I have it in my notes, is to explain the two types, kind of the break at the asteroid belt. We have the rocky planets ending with Mars, and then we get the gaseous planets beginning with Jupiter. Like, how did that work? So we call them terrestrial and Jovian planets, respectively. And then we didn't hit a slide on this yet, but it's so cool. We need to kind of talk about what's called the leftovers. In Unit 3, I think it's Unit 3, we're going to talk, we have a chapter that talks about comets and asteroids. Okay, but basically I call them crumblies. They're not as big as a planet, right? But they're definitely there. And the crumblies that are in, how do I say this? The crumblies that are pretty far off have not only a rocky component, but they're also icy. So just to kind of give you a heads up, the two regions that we kind of find crumblies out there are in the Kuiper Belt and the Oort cloud. Okay, Kuiper Belt and the Oort cloud. I don't know if you remember, but I talked about the Kuiper Belt when we talked about Pluto, the Kuiper Belt, kind of the plane of the ecliptic. Actually, Pluto is just a Kuiper Belt object, affectionately known as a KBO, Kuiper Belt object. And so is Eros. And then we have this Oort cloud. Oh my gosh, it was like this just crazy spherical thing of stuff, icy rocky crumblies that are associated with gravitationally with our sun. Okay. So another couple things to kind of take into consideration. Observations of we just know this is how it is. You know, I said Uranus is like this, okay? And then the other thing is our moon is anomalous. Our moon is an exception, okay? I mentioned Mars has a couple of ugly-looking planets. Mars has a couple of ugly-looking moons. But Earth's moon is just crazy. And there's an explanation for that. So what I'm going to talk you through, remember what a theory is. Kind of put theory. You guys on your tests recently told me that hypothesis is not the same thing as a theory. So when we talk about astrophysicists coming out with a theory of how our solar system was formed, don't just say that's a hypothesis. Okay. So it's called the nebular theory of how our solar system was formed. So we've run into the term nebula before. Nebula is basically you're in outer space and you run into a pocket of stuff. That pocket could be gas, dust. That's a nebula. And there's different reasons to have a pocket of stuff up there. Most of outer space is basically nothing. Okay, but you run into nebula like, oh, I could live here. And as it turns out, nebula are great for forming stars and system of planets around those stars. Okay. So the word recycle means to kind of reuse. Okay. Use something and then reuse it. So the idea of galactic recycling, and actually I think I would change that to stellar recycling. I kind of like that term better. Of course, stellar meaning stars. This is kind of showing you how a star can recycle itself. This right here, I'll kind of start with the kind of, you see the jets of energy kind of coming out of the center of something. This is a baby star. Batty? This is a baby star. And this is jets of energy, and we'll kind of talk about why those jets of energy might be coming out of a star that's being born. Okay? But we see stars out there kind of like that, or baby stars, not even kind of turned on stars. This is a full-fledged star, okay? And like we saw on the slide earlier about our star, the sun, this is actually creating its own energy via nuclear fusion, okay? So this is a full-fledged star. And in its core, it is converting energy, or creating energy according to this E is equal to mc squared in its core. Well, we're going to talk about how stars don't live forever. I don't know if we want to tell our children that or not. Okay. Down there at the bottom, I'm just going to say a star ages. Ages/dies. That's one of the things that we'll talk about in this class. Kind of how will our star age? And how do other stars age? Okay, and it depends on how massive the star is. Our star is going to kind of age and go out gracefully. Okay, our star in about another 5 billion years. Our star is just going to kind of, well, I say gracefully, it just won't blow up. But what our star is going to do is swell, basically, in another 5 billion years. It's going to swell. And it's going to swell beyond the orbit out to the orbit of Jupiter, if I'm remembering right. So that means we'll be toast. So between now and 5 billion years from now, we need to figure out where we're going to go. I think we will. Okay. But, so we're going to swell, and actually this works for us. This is actually, to a small amount, when we swell, we are going to kind of, near the end of our life, kind of, our sun will give off gracefully its matter back to its surroundings. And it will create a nebula. And within that nebula, you need more than that material to create a new star, because it's still got a lot of mass right here. And when it finally retires, it'll be a white dwarf. If you've heard of the term white dwarf, it's kind of a retired star. It's a star that no longer has creating energy in its core. So that'll be okay. White dwarfs, though, I will tell you, they shine for a while just based upon the energy they built up when they were alive. White dwarfs eventually will cool down to become a brick. Okay, because they have no more. Okay, so that's us. But more massive stars, and we're going to see kind of the cutoff is 8 times the mass of our sun, and there's a lot of those out there. If it's more than 8 times the mass of our sun, then it goes out with a bang. Supernova, yeah, okay. And to me, especially the ones that go out as a bang, okay? When they go out as a bang, they take their guts and they, okay? And they create what's called a supernova remnant. And this stuff could be fodder for a new star to be born. That's my point here. That's the whole recycling thing. Okay, so if you're good with that. So think of a star blowing up at some point before 4.6 billion years ago, okay? Probably more like 6 billion years ago. Think of a star 6 billion years ago went supernova. Okay, it left its guts out there for us to be formed. Okay, then enters what we call the solar nebula. That's ultimately going to become our solar system. So we talked about things that spin. And if something spins like a skater, okay, if something spins and if that something goes ahead and changes the distribution of their mass, like you see here, kind of instead of going out like this, coming in like a skater draws her arms in, it goes faster. So kind of early on, this blob that's going to become us, our solar system, had that rotation, and as it came in, it went faster and faster. Okay. And as it came in, went faster and faster and faster, kind of it slung and kind of made that ultimately what's going to be called our frisbee, the plane of the ecliptic, okay, where the track that all the planets are going to orbit the sun on. So that's kind of from the solar nebula. We flattened and went faster and faster. Okay. So the term, and I'm going to show you some slides here of some photographs of other stars kind of caught in the act of being formed. And other stars out there that may or may not have the jets of energy kind of coming from them, like we saw a few slides ago, kind of have this disk thing going on where planets can form. So if you have a prototype, you have kind of the thing before the thing, right? So a protoplanetary disk is where planets can form. We see that in other stars. Okay, so this is actually just kind of showing you, if I were to animate this, when things contract, they go faster. Conservation of angular momentum. I'm going to show you this one. And this is kind of cute. This one reminds me of bumper cars. and watch the green bumper car, okay? So basically this is kind of trying to show you how matter kind of eventually kind of keeps going the same direction. Doesn't it look like bumper cars? So eventually the number 14, car number 14 is brought into line. So kind of think of that as what was random eventually kind of falls into line. Play this one. So this is going to kind of, I'm going to dim the lights. But this is looking at it face on and edge on our solar nebula again. See what you think. It's kind of hard to see, it's subtle. So edge on and oblique is face on. So you see it kind of thinning out and going faster and faster and faster. I think you're getting the idea. This is the one we saw. I think I have too many slides on this topic. Okay. So, I guess it's not helping. I just need to tilt that projector down. I was going to see if my NASA's eyes ever came up. Well, NASA's eyes would show you similar information here, but I'm just going to show you this information. The back of your textbook has this information too. Kind of you recognize across the top there. I'm going to kind of click across the top there and see what differences you can see. So, for instance, I told you the sun is spinning counterclockwise, right? And there's its axis of rotation. It's not straight up and down to the ecliptic. It's tilted just a little bit. This is kind of fun when we talk about the sun. We're going to see that it rotates once every, it's about 4 weeks or so. Almost, 25 days. Well, let's go on to Mercury. Mercury, straight up and down. Good for him, her. Okay. You can kind of see some other pertinent information about Mercury. Again, there's a pretty good table in the appendix of your textbook. All right, now look carefully. I'm going to click on Venus. See if you see anything different about the red See that red arrow? Okay. So that was Mercury. Oh, you're like, dude, talk about a rebel. So in order to talk about that Venus, I'm going to remind you about Uranus. Okay. Uranus, we said, was like this, right? Venus is basically got hit so hard, we think, it's like this. So its tilt is almost 180 degrees, 177. So full like that, that would be 180, so it's 177. So you know what that means. If we look at what we think is like the North Pole of Venus, it's going clockwise. Okay? It's like spinning backwards. It's called retrograde rotation. It's crazy. And then, of course, we have the Earth. Everybody knows about the Earth. And then Mars, etc. So I think that's neat. So all sorts of different characteristics. Okay. Who's got their slides? No one has their slides.
They weren't there. They were printed off about 15 minutes before class.
Bless your heart. Bless your hearts. You guys should tell me these things. Okay. Well, in that case, let's just stop for the day. We're going to pick up here, and I'll make sure I make those available. So, yeah, feel free to let me know if they're not there. Okay? But anyway, that's a good stopping spot. So have a great weekend. And I will post those.